Hello everyone, it's Sumit, and in today's session we're going to learn about linear regression. So before jumping into the linear regression, I'm going to give you a brief outline of what we're going to cover up in today's agenda. So first I'm going to give a brief overview of what is linear regression. Then we're going to understand the linear regression both mathematically and programmatically, like how we can solve it. Then we're going to jump into the evaluation matrices where we're going to find the loss function using the mean absolute error, mean square error, root mean square error, and r square. So by these four ways we're going to find the loss function, or we can see the evaluation matrices of the linear regression, what we had predicted, like how accurate it is. Then we're going to jump into the use case of linear regression where we can see the live application, live use case of it, like where we can apply this linear regression algorithm in real world. Then at last we're going to jump into the live coding session where we're going to see the two use case. First is with the house rate prediction. We're going to predict the price of the house based on our housing data. Then the second would be e-commerce web app prediction, where we're going to predict whether, as an like the manager or the something, we need to go with either with the web development or the app development, where the user likely to spend most of his time, whether in the web or app. So we're going to predict like whether it's with the web or the app. We need to go for the development. So this is what we're going to cover in today's session. So let's start with it. So what is linear regression? So linear regression is in a form of predicting modeling technique where we used to predict the value of an independent variable based on value of an independent variable. So what is my dependent variable? The value what we wish to predict. Normally what we draw across y-axis. And what is my independent variable? The value, the variable which we can say we used to explain the dependent variable. Let's say, let's see this diagram. So in this diagram, this blue points are my data points, you can say, and this red line is my best fit line. So this is an equation of linear regression. So which means, so that is like y of I equals to beta naught plus beta 1 xi, then random error term. So what is y of I? So this is my dependent variable which we normally draw across y-axis. This beta naught, where my best fit line cuts in the y-axis, like from the origin we can find the intercept of it, which we call as an intercept or the beta naught. Then we have like beta 1, which we normally call as a coefficient. Then we have x of I. This is normally called as an independent variable which we draw across x-axis. Then we have the random error term. Normally in most of the cases random error term is 0, but we used to keep this random error component to basically analyze like what is my, like what, how we can derive the accuracy of this particular equation. And then let's move on to understand this more diagrammatically. Let's say I have data points drawn on my graph. Let's say I have n data points drawn. Then we want to find the best fit line, or you can call as the regression line. Once that is done, other tasks would be to find the predicted value or the estimated value. Once my point is estimated, then we have to find the distance between the estimated value and the actual value. So the best fit line would be the one which will be having the least number of errors, or which would be having the least distance between the predicted value and the actual value. If not, then we need to see how we can minimize this error. Now we're going to see mathematically how we can use the linear regression algorithm to find the best fit line. So if you can remember, in my previous slide I told you the equation of linear regression. So that was like y of I is equals to beta naught plus beta 1 xi plus random error component. So as I told you, so this was my dependent variable. This would be my coefficient beta 1 and beta naught would be my intercept, and x obviously would be my independent variable. So now most of the people get confused by looking this equation, but we are about to simplify it. Then in very simple terms, it would be y equals to mx plus c. I believe like most of us had used this equation in our school days itself. So now I'm going to move to the snip view where I can explain you better. Yeah, let's say I have the data points like 1 comma 3, and these 5 data points which we have. First we're going to plot that on the graph, let's say on the 2D graph. So first our data points are 1 comma 3. So this is my 1, this is my 3. So this is my first data point. Second data point is my 2 comma 4. So first we want to consider only on this x and y. First we need to plot only this data point on my graph. So first 1 and 3 we had drawn it. So this is my first data point. My second data point is 2 comma 4. So for this 2 comma 4, this is my the second data point. Our third would be 3 comma 2. So this is our 3 comma 2. This is a third data point. Next is 4 comma 4. This is the fourth data point, and the last is 5 comma 5. So this is the fifth data point. Now based on this available data points, which we normally get it from in form of data or something, like what were the available data you can say. So based on this available data, first we need to find the coefficient of it. So as you all know, so this is a coefficient and this is our intercept, so where it normally cuts. So for the coefficient, so the equation of the coefficient is summation of, like what we normally say as m equals to summation of x minus x bar into y minus y bar divided by x minus x bar whole square. So what is my x bar? X bar is my mean of all my x data points, like whatever the data points are available in x independent variable you can say. So this we normally consider as my independent variable, and whatever we are plotting on the y, we can consider as an dependent variable. So now we have an independent variable, dependent variable, and the equation of our coefficient. So to calculate the equation the coefficient, first we need to find x minus x bar. So before calculating x minus x bar, the first thing would be calculating the value of x bar. To calculate the value of x bar, so we want to find the mean of it, all the data points available in x axis. So now what we have, 1 plus 2 plus 3 plus 4 plus 5 divided by 5. As we have number of data points is 1, 2, 3, 4, 5. So we are going to sum up all this data point divided by 5. So that is 1 plus 2, 3, 3 plus 3, 6, 6 plus 4, 10, 10 plus 5, 15, 15 by 5, that is 3. So mean of x is 3. So once we got the mean of x is 3, then we can calculate x minus x bar. So the calculation of x minus x bar would be 1 minus this 1 minus 3, that is minus 2, then 2 minus 3, that is minus 1, then 3 minus 3, that is 0. Similarly, that is 4 minus 3, 1, then 5 minus 3 is 2. So once we got that, similarly in that fashion itself, we're going to calculate the y bar. So that would be 3 plus 4 plus 2 plus 5 plus 4 plus 5 divided by 5, that is 3.6. So the mean of y is 3.6. Now we can calculate y minus y bar. So the y minus y bar would be 3 minus 3.6, that is minus 0.6, then 0.4 minus 1.6, 0.4 and 1.4. Once we got this, the next would be the calculation of x minus x bar whole square. So we had already calculated x minus x bar. We're going to do the whole square of it. So minus 2 whole square would be 4, minus 1 whole square would be 1, then 0 whole square would be 0, then similarly 1 for the 1, then 2 whole square would be 4. Once we got that, then we're going to multiply x minus x bar into y minus y bar. So once we got that, then we're going to multiply this x minus x bar into y minus y bar. So the multiplication of minus 2 into minus 1.6 would be 1.2. Similarly, this minus 1 into 0.4, that is minus 0.4. Then 0 into minus 1.6, that is 0. Then 1 into 0.4, that is 0.4. Then 2 into 1.4, that is 2.8. Once we had got that, so once we had got that, then we're going to find the summation of everything. So the summation of this would be 1.2 plus 0. Plus minus 0.4 plus 0 plus 0.4 plus 2.8. So as you can see here, so this 2 will going to get cancelled out, plus minus 0, then 2, 4. So this equals to 4. So the summation of this would be 4, and the summation of x minus x bar whole square would be 4 plus 1 plus 0 plus 1 plus 4, that is equals to 10. So we got coefficient, let's say m as 4 by 10, which is equals to 0.4. So our equation was y equals to mx plus c. So once we had got that y equals to mx plus c, so the next would be calculating the intercept. So how we are going to calculate the value of c? So as we already calculated the mean value of x and the mean value of y, so based on this, if we put y as 3.6 and the x as 3, then if our intercept is like 0.4, then if our coefficient is 0.4, then based on the coefficient we can find the intercept as 2.4. So now we got the value of c as 2.4. Once we got the value of m and c, then we have all the data points available. For this we can predict it. So let's say now I got our equation would be y equals to 0.4 x plus 2.4. So this is like knowing uh, calculating the coefficient and the intercept. Now we're going to see how, based on this calculation of the coefficient and the intercept, we can predict the value of the dependent variable, like all the values of y, what we need to predict, how we can predict the value of all the data points available for the y. So let's look into it. Let's say for the given value of an coefficient m is 0.4 and intercept for 2.4, what we had calculated right here, then based on this we have an equation y which was y equals to mx plus c. We know the value of m, we know the value of c, which is our intercept and coefficient, and now we have all the data points available from which we had calculated. So now based on this data points like 1 2 3 4 5, so based on this data point like 1 comma 3 2 comma 4 3 comma 2 4 comma 4 and 5 comma 5, so for this value of x we're going to find the value of y. So one by one we're going to put this value of x for all the available data point. We're going to put that in the equation as y equals to mx plus c, and then we're going to find the value of y. Once we're going to find it, then we're going to plot that in a graph, and then we're going to draw the best fit line across it, so which we're going to cut at 2.4, which was our intercept. Once we found that, then we're going to find the distance between the actual value and the estimated value, like what we had got it. Then we'll see in next video, we're going to see in next slide, we're going to see like how we can minimize this error. Once we had predicted the value of y across all the given data points, then we're going to see the how good was our accuracy, like how well, like what we had predicted, how good it was. To get that, we need to know like what is evaluation matrices. So basically evaluation matrix is a technique that is used to judge the performance or let's say accuracy of your model. So there are different types of evaluation metric like mean absolute error, mean square error, root mean square error and R square. So now we're going to see both mathematically and programmatically when we're going to cover up in the live session like how we're going to call an scikit library to calculate this and mathematically how we can solve it. Let's start with the mean square error. This mean absolute error we're going to cover up in the coding session. We're going to do it using the scikit library. It's an very basic, then like I'm not covering this in this particular video. I'm directly starting with the mean square error, then we're going to go in the root mean square error, then we're going to see R square mathematically, then we're going to see programmatically how we can call this API to calculate all this metric evaluation. Let's see. So the first evaluation metric what we're going to cover up is that is mean square error. So mean square error is basically tells you like how close a regression line is to the set of points. It does this by taking the distance from the points to the regression line and squaring them up. Squaring is necessary to remove any negative sign. It also gives more weight to your large difference. Let's say in green we have the actual data set which we had plotted, and in brown we had the estimated data set. For this particular given data point, like for 1 comma 2, our estimated is an upward trend, like it is in the same x coordinate but is in a upward trend, so that is positive value. So for this like it works, and that is an this is a predicted value. But for this case, if you can see, our actual value is like something around 2.1 by 4, and the estimated value that is in downward trend. So for this we always used to square them up. That's the reason I told you, so we need to square them up, and it also add more weightage to your model. The smaller the mean square error is, the closer you are to find the line of best fit. Depending upon your data, it is very impossible to get the very small value for the mean square error, but it would be always closer and it will always give you the best estimate for your model. Let's see mathematically how we can calculate the mean square error. So the equation of this standard error of estimate, which we call as a mean square error, is under root of summation of y cap minus y whole square by n minus 2. So let's say we have the data point as 1, 2, 2, 4, 3, 5, 4, 4 and 5, 5. For this, if we need to calculate the cap of it, so the cap of it is my predicted value. So for this, my predicted value, let's say my predicted value is 2.8. So this is my y value, original value, and this in brown, which that is my predicted y value. Let's say y of p or y cap. Now we need to calculate y cap minus y. First we're going to do that, then we're going to do y cap minus y. Similarly, we're going to find the value of all the data points, let's say y cap minus y for all the data points. Once we need to calculate that, we need to do y cap minus y whole square. Then we're going to do the square of this points. Let's say 0.8 whole square is 0.64 minus 0.6. If you are doing the square of it, this negative sign we are removing it, that is 0.36. Similarly for minus 1, that would be 1, 0.6, 0.36, 0.2, it would be 0.04. Then we need to have a summation of all the data points. Then we have, after doing the summation of it, like 0.64 plus 0.36 plus 1 plus 0.36 plus 0.04, that is 2.4. Once we have the 2.4, the number of data points as per my available plotted data set is 1, 2, 3, 4, 5. Let's say we have the 5 data points like 1, 2, 2, 4, 3, 5, 4, 4 and 5, 5. So for this 5 given data points, I'm going to do a n minus 2, which is 5 minus 2 is 3. So 2.4 by 3 is zero point 0.8. So the under root of 0.8 would be 0.89, which is my mean square error. So I'd already told you it's very impossible to get very small amount of mean square error, but the smaller the mean square error is, the model of your accuracy is more accurate. Once we found the mean square error, similarly we can find the root mean square error just by squaring them up. So now we're going to jump in knowing what is r square, which is our last evaluation metric. So R square is an statistical measure to show how close our data are to the fitted regression line. Let's see, for the terminologies, we have y as actual value, y bar as the mean value of y, and yp as the predicted value of y. In understanding more, let's say this is about the predicted value, which has been shown in brown points. It is my predicted value. For this predicted value, we have drawn the regression line, and this is the mean what we had got. So the main motto of this R square is to find the distance between actual minus mean versus predicted minus mean. Let's see the mathematical explanation of it, like how we can do this. The formula for this R square is summation of yp minus y bar whole square by summation of y minus y bar whole square. So this is nothing but the distance between the predicted value and minus mean by actual value minus mean. Let's say for this data point, what we had got there, we can easily find y minus y bar. So y minus y bar would be y, this is my 3, this is my 3.6, which is my y bar. So 3 minus 3.6 is minus 0.6. Similarly 4 minus 3.6 is 0.4. Similarly in that way minus 1.6, 0.4 and 1.4. So now we had got y minus y bar, which is our this value. Now we need to calculate, now we need to do a whole square of it. Then we're going to do a simply whole square of it. So minus 0.6 whole square is 0.36. Similarly for 0.4 is 0.16 and so on. We're going to find it for the other data points. Once we're going to find it, we're going to do a summation of it. We're going to add 3.6 plus 1.6 plus 0.16, then 2.56, then plus 0.16, then 1.96, that is 5.2. Now we got the value of actual value minus mean value. Then we're going to see, as we had calculated before, this is our yp, which is our predicted value, that is 2.8, 3.2, 3.6, 4.0 and 4.4. Similarly, in the same way, to calculate the distance between the predicted value and the mean value, we're going to do a yp minus y bar, that is yp is my predicted and y bar is my mean value, that is yp, that is 2.8 minus this is y bar, right? So my y bar is 3.6. So 2.8 minus 3.6, that is 0 minus 0.8. Then 3.2 minus 3.6, that is minus 0.4, and so on for the other data set. Then we're going to do a whole square of all the data points, and at last when we're going to do a summation of it, we're going to do as 1.6. Now we got the summation of this as 1.6 and summation of y minus y bar whole square is 5.2. So this is our r square. Now if we have for the available data point the less number of the less value of the R square we get, the more accurate our data point is. As I told you, the R square does not indicate whether the regression model is accurate or not. So you can have low R squared value for a very good model or very high square value for a model that doesn't fit the data. So now let's move on to understand the evaluation metric R square, which is the quadrant of fittest. So let's say if our R square is 0.3 for the data set available, which lie across this plotted graph, and this if that is 3.3. Now if we increase the value to 0.7, the data points will come more closer. Now again on increasing it, the value will come more closer, and again making as 1, it would be on the same line as the best fit line. But if our data points are too far from this regression line, let's say we can treat this as an outliner, so the value would be too less. So what does that mean is, if we are decreasing the value of the R square, then in that case it will going to affect the value of the all the data points. Let's say I have lot number of outliner available for my data set, then the accuracy of the model will not fit to it. So by now we had already understood like this linear regression model predicts the continuous variable and completely rely on polynomial. So the less number of outliner we have in our data set, the more the accuracy of our model is. Let's see the difference between this mean square versus R square. So basically for this mean square, what we had understood is like we always used to calculate the distance between the predicted value and the estimated value, and or the actual value. Let's say this over, this is my actual data point, this is my predicted data point. So we normally find a distance between this actual and the predicted one. But whereas in case of R square, we need to know the mean of the y-axis. Based on this, we find the distance estimated between the actual mean and the distance estimated between the predicted mean. So this is my predicted mean, this is my estimated mean. So whatever the distance we calculated, so that is always lies around with this mean. So here in this mean square we find the distance between this, but in R square we find the distance between the actual distance and the mean of the line, and the distance between the predicted and the mean of the line. Based on that we calculate the R square. Now let's see the use case of this linear regression. So basically this model, we can use it in our business to evaluate trend and for the sales estimation. Then we can analyze the impact of the price change or accessing the risks. Let's say for advertising, like I'm spending on the advertisement, so that would be have a direct impact on the revenue, which is like my continuous variable. Like for the drug doses which are like which anyone is taking, that would be have direct impact on the blood pressure of the patient. Similarly, the amount of fertilizer which we are adding to the soil and the water, that would be particularly dependent on the crop yield, and same as the different training regimens have on pillar performance. So the less number of outliner, let's say in this diagram our data point is so scattered and data points are too much away from this linear regression line, so we are about to get the like we won't be able to get the best accuracy of this predicted model. But whereas in this diagram, if we have the like all the data points is been lies very near to the regression line, in that case it would be we would be tend to find the good accuracy of the predicted model. So now let's start with the coding session with the Python, where we will going to see the two use cases. First, with the house price prediction. Based on the housing data, we're going to see like how we can predict the value of the price of the house. And the second would be based on the data, like for example how much time I spend on a particular website. Let's say, take an example of the Flipkart, like how much users spend time on website, or how much order do I get from the app, what are the offers do I have in app, and the same the relevant offer, how much I am getting if I'm ordering from the website. Then based on that, how much should I, as an owner, how much should I predict, or how much should I invest either in my web or the app, based on my users, like based on my users thing, like how much user has been spending time either on my web or app, whether I can predict, like either I can go with the app or the web, like which is more good. So this we can predict. So all this we're going to do, like whatever we had learned mathematically till now, so based on that, whatever the mathematical equation what we had seen, based on that we're going to do everything using the scikit-learn library, which is available in Python. So for that, first we're going to pre-process the data. Like let's say we have got a huge data. Now we need to see like is and how good our data is. Is there any null value across either in any of the rows or any of the column is available? We need to remove them out. Then we're going to visualize the data using the matplotlib in 2D. See like different kind of charts, a graph, like how good our data is. Then we're going to create and train the linear regression model. Once that is done, then we're going to find the best fit line by predicting the data points. Using the data points, we're going to predict the value of yp, like what of the dependent variable we can say. Once that is done, then we're going to find the metric evaluation, like how good my prediction is, like how the accuracy of my prediction of the model is. So this we're going to find everything using the API introduced by the scikit-learn, which we are having in Python. So let's move on to the Python IDE to see all these examples. So the first use case what we will going to cover up is the house price prediction. Let's say for this, first I will going to import all the libraries. Once my library had got imported, then I will going to load all the data which I have and hold it in one variable. So once I hold that, then I will going to check the head of it to check the entire data frame details such as rows and columns. So let's do this. So on executing this particular head, then I would be knowing, like for this particular house, let's say for 0, the average area income is around 79,545, average house age is 5.6 years, the number of rooms is 7, average number of beds is 4.9, price, population, and the address of it. So this way we know the entire data of it we can check. But to get it in the more info, we can do housing data.info. If we're going to execute this part, then we would be knowing the total number of entries in that particular data set, like from where we had loaded. The total number of entries is around 5,000. The number of data type of each of the columns, like for each of the column it has been represented as a feature. Let's say the x access, like let's say we can call as an independent variable. So this is like from the info we used to got, like for all the columns, like what is the data type is there, number of null count is there, how much, and the total number of entries are there, the number of columns. Once that is done, we're going to go and do the housing data dot describe. This basically will going to give us the statistical data of the entire column. Note that, so in the first one, when we did the head, we got address as a column, but in the statistics data, that address column is missing. So by this statistical data, by doing as housing data dot describe, we're going to know the count of it total, then going to mean, standard, mean, 25%, 50%. This way we can get the statistical data of that particular housing data. Then I'm going to go and execute the housing data dot columns. On executing columns, I would be getting the number of rows which are present with the names, so that I can check, like for this first column there's a space in between the number of names, the number of character you can say for this entire word, or for average area income there's a space, there's a dot. So all those things for the name, for checking the name of that particular column, I can check by doing housing data dot column. So once I check with my data, and I did some kind of exploratory analysis on my data. Once I did that, so now I'm going to move on going for the data visualization of it. So for data visualization using the Seaborn, like this we had imported as a Seaborn. If you can remember, the first thing we did, import Seaborn as SNS. So when we're going to do as SNS.pair plot, the first thing we're going to come up is the histogram, correlation, and the scatter plot. So you can see this histogram, the correlation of data, and the scatter plot. So this is basically my scatter plot, this is my correlation of data, and this histogram. So you can see like my the number of average area, number of bedroom that has been segmented into 1, 2, 3, 4, 5. And it would be in 5, because like for this data, the average area of the number of bedroom, it cannot be 2.5 or 3.5, it has to be segmented. So this data is actually correct, so it has to be 2, 3, 4, 5, 6. That would be the int value. So this we had got from this data. We can analyze it through SNS.pair plot by just passing the entire data frame to it. Then we're going to get this pair grid for this plot. Once that is done, we're going to plot the pricing of it. Then we're going to go ahead and check the pricing of it. So to check the price, when we're going to do that, so once we're going to do analysis on the price what we are about to predict, they're going to see the average price of the houses lies between 1.0 to 1.5. This is in millions. So it's the average price lies around 1 million to 1.5 million. So where the highest graph is there, the highest mapping is there. So based on this distribution of the price column, we can actually explorate the more on this pricing data. So once that is done, we're going to move ahead, and then we're going to see the correlation of all the column. So to see the correlation of column, first I'm going to show you if I do the correlation of the column. So this is statistical kind of data first. So now we are seeing this, this one is going in this diagonal direction, and it has to be diagonal because this price is been matched with the price in the last column. So the data would be always in this type. So this would be my statistical column. So when my all data is there, so now I'm going to do a kind of plotting of this data using the heat map of Seaborn. So now I'm going to pass the entire data frame correlation with an anode equals to true to see like in my I'll show you this one. Yeah. So this, if suppose in case if I'm roaming this as anode equals to true, this value which I'm seeing here, I'm not able to see it. I won't be able to seeing this value anymore. So yeah, so this is the thing. So basically this you can see there are a lot of gray and low correlation value which are here on passing this anode as true. We're going to see the value of it, like which are all the value are low. Then this is a one like which it would be actually this price would be comparing with the price in this area, average area income would be comparing with the average area income. In that way it would be one across the diagonal. So once that is done, we had did with the kind of analysis with the data visualization. Then we need to move ahead and going to train our linear regression model. But before that, we need to split our data. To split our data, first what we need to do is we need to do first we need to check the number of columns of it, like what are the columns are there. So once I'm going to find it, then I'm going to comment it. So this is the number of column. Then I want to actually copy this part, like till where we want. I want to copy this part and I want to paste it. Now you can see this housing data which I'm carrying in my, which I'm storing in my X. So number of independent variable which I am storing as, like for the X you can say, so that is an average area income, average area house age, average area number of rooms, average area number of bedrooms, and an area population. I am excluding the address here, which is not needed by me, and the Y value which I am about to predict, like the dependent variable, so that I am keeping as a price which I am about to predict, that I am storing this separate Y. So this would be my X and Y. So once that is done, I'm going to execute this part. Yeah. So once I'm going to store like what are the independent variable is there in the X and the dependent variable in the Y. So once that is done, now it's time to split the data. So it's always a good practice to split the data in certain parts, like in what percentage, like if out of 100, on 40% of data you want to test it, and on 60% you want to train it based on the available data set. So for that there's already a module available. So from the scikit-learn sklearn.model selection, you can import this module train test split to basically check this, like with the functionality of it. To go into the deep of it, you can do a shift tab on this, and you can basically expand this to see like what all the documentation of it's available in Jupyter, and there are a few examples of it, like how it can be done. I'm going to show you in Spider as well, like how this we can see. I'd installed kite there, so I'll show you that one. So this you can see, like this X train, X test, Y train, Y test. So this way we are about to use this. This is a particularly the example given, and we can use that in this way. So I'm going to copy paste this, so which I'd already did. So I'd copy pasted this entire thing, and the random state I'd made is 101. This you can keep, and this based on the example you can keep, but I am recommending you to make it as 101, just because to have the same result in case whichever the data I am sharing you. So on that data, to have the same result or the same prediction, you can have this as 101. This test size predicts the percentage of data, like from out of data, how much you want to test it and how much you want to train it. So my training data size would be 60%, my testing data size would be 40%. Based on this, it will going to split up my data. This X would be my independent variable, Y would be my dependent variable. So like for each X, it would be, for this X itself, it would be having X train and X test, and for this Y it would be having Y train and Y test. So once it will going to split this, I'm going to run this part. Yeah. So once I'm going to have this variable, once this had got splitted, then we're going to move on creating the model. For creating the model in Python, from this scikit-learn, we can actually use this scikit-learn. From this module, we can directly import this particular module called as linear regression, and we just need to instantiate this part, like we just need to initialize this, like kind of linear regression. So once this part is done, like if I'm showing that in an lm, in that case, if I'm going to do lm.fit, so what it will going to do is, so I'm going to execute this, then lm.execute. So once I'm going to do lm.fit, it will going to give me, so this fit had already occurred with X train and Y train, which means like I am passing X train and Y train data to fit in that particular model. So I am training with that. So my training of that particular data with this linear regression is done. So once that is done, so I've got the LM of it, I got the model of it, then I'm going to check the intercept of it. So what was my intercept? So basically when I was explaining you y equals to mx plus c, so c was my intercept, and to know the c of this model, I can directly call lm dot intercept underscore. So I'm going to call this, yeah. So on calling this, I got the value of this particular model, like the value of c. Once I'm going to get that, once I get the intercept of it, then I'm going to go ahead and going to find the coefficient of the model with all the features. Let's say coefficient in the sense, I'm going to put this part, yeah. For this part, if you're going to run it, so I got some issues. Coefficient is no coefficient. Okay, I missed this underscore, yeah. Yeah, so now for this coefficient, you can see I got the values of for all the co columns. You can see for all the columns, let's say as a feature, we got the coefficient of the model. So let's say for the different values of this, like for average area income, for average area house age, for average area number of rooms, for average area number of bedrooms, and area population for 1 2 3 4 5. For this 5 column, we got the different coefficient of it. So once we got the coefficient of it, now we need to interpret the coefficient, like what is my coefficient, how can we can interpret it. So basically to interpret it, the first thing what we're going to do is we're going to put everything in the pandas, like we're going to put the entire data, we're going to use the data frame. So for that we're going to pass the entire coefficient with the column, and we're going to make the columns as an coefficient. So let's execute this part. Oh, again I missed something. X is not defined. X is x, right? No, this is small x, so this would be small x. Yeah, so now you can see I got the coefficient. So once I want to run it, so I got the coefficient for this against all the features, like example average area income. My coefficient is 21.52. For the average area income, the coefficient is this one. For the average area house age, for the one for per rise in average house area, my coefficient is rupees 1,64,883. In the same way, for in one increase in number of rooms, so it would be around 1,22,368. So in the same way for the number of bedrooms and then area population. So there I had included that in the comment, you can go and check. In case this area, this all data depicts this, this is based on the dummy data. In case you want to go and check, you can check with the Boston data which is available. You can, from the scikit-learn, you can import this Boston module, like load Boston. So this will going to import you the module, and from there you can directly access the entire data set for this housing price prediction. You can try with your own this part. So once that is part is done, and you can take that entire thing in the data frame itself. So once that is done, you can visualize all those things which I did before with that Boston data set. So once that is done, so once you find the intercept and the coefficient of it, so now it's time to predict our model. Now we need to find the value of y, like we need to find the value of y. Not till now we found the value of m and c, like from y equals to mx plus c we found the intercept and the coefficient. So once we found the intercept and the coefficient, now it's time to go and find the value of Why? Let's say we need to predict the model. To predict the model, basically what we need to do, we for all the values of x, like what we have, like let's say for the x test, what we had split it in the data, for that we're going to check it, we're going to test with that. So we're going to predict based on that, and it would be, we had like we had already predicted and stored in the prediction. So this is my prediction variable where we'd already stored it. So once that is done, we're going to move ahead, and we're going to do a kind of a scattering plot where I can show you, like based on my y-test, which based on my actual value and my predicted value. So this y-test is my actual value, which we call as an unseen data, which we can even call as an unseen data, this x-test, and this prediction would be my predicted value, which we had already got. So from this, if we are about to plot this graph, then we can see, so all my data points like lies around my best fit line. So most of the data point lies around this best fit line. There are no outliers, like there are no such kind of data points available on very off that data, like if suppose the data points are present in, let's say at this point, this point, or this point, or very off from this particular regression line, then we can say that as an outliner. But in this case we don't have that much of outliner. Most of the data have been near to my regression plane. We can say that it's a good plotting. So based on this, we actually see like what the model we are about to use, whether that is correct or not. So next what we're going to do is we're going to go and find the residual histogram, so which would be the actual distance between the actual value and the predicted value. So for that we're going to plot a diagram, and we're going to see based on this plot if it's uniformly distributed. So let's say I pass here, so this plot which I'm about to do it, so for this plot using Seaborn, I am just doing actual value minus predicted value. So the prediction is my predicted values. So if I'm going to run this, so you can see here key all my let's say my price distribution across, like it's been uniform, which means like whatever the data we had used for this, from this only we can decide if we had used the model for this kind of data set, whether that is correct or not. So we can see here like the price is like uniformly distributed, so we can say like it's a good choice for this data set, this model is a good choice for this data set. So once that is done, is now to see like the accuracy of the model, like whatever the prediction we had did, whether that accuracy, how much correct accuracy is there, if there is any error there, let's say as the loss function, how we are able to minimize it. The less the value of this kind of all the loss function, the more accurate your your model is. So previously in our slides we had discussed there are four kinds of metric evaluations. So for that it was there like mean absolute error, mean squared error, square mean error, and the R square. So that time I told you like I would be concentrating on this part, because this part that time I didn't explain you, like for this it's a very simple equation, we can directly go and find it. So I didn't explain this mathematically, I'm going to explain you here programmatically how we can do this. Then the next is a mean square error, where we had found that like how to solve this mathematically, this both part, and we have seen the R square. To do all this programmatically, sklearn, like for the scikit-learn, already give you the module called as matrices. So inside this matrices, you directly need to go and import this matrices. Let's say I'm going to import this matrices. Once I'm going to import this matrices, and once I'm going to call this, let's say once I'm going to call this matrices dot mean absolute error, directly it will going to pass the value for this. Like for this I need to go and pass y test, which is my actual value, which is like kind of unseen data, and this is my predicted value. So once I'm going to pass my actual value and the predicted value. I guess I had already explained the actual value and the predicted value in the previous slide. So once I'm going to pass this actual value and the predicted value, so then we're going to find the mean absolute error. In the same way, for the mean square error, for the root mean square error, for the root mean square error only we need to just do the square root of the mean square error, whatever the value we are getting at here. And in the same way as the r square, how we need to calculate the r square. So r square, like for the RMSE, which we often call as the root mean square error, that is like one of the, it has been more popular than other than three of the metric evaluation which is available. So for that, like, it determines the less the value of this r square, the more the accurate your model is. So by this project, we had actually predicted the value of the house. We had did the prediction based on the data set. We had splitted the data set. I'm going to give you a quick overview of like what we had learned just now. Let's say in a spider, like, yeah. So what we had did is, so first we had imported the libraries. So first we had imported the libraries. So once my library got imported, then we had tried using reading the data through a CSV file. So once my, so you can check like whatever I'm executing it here, you can see it here. So once I did the housing data, once I had the housing data, so you can see like for this housing data, this is my average area house. This is actually this I'm doing in Spider to show you more graphically. Yeah. So for this index 0, average area is 68292, average area house is this much, and even I can sort it out. Yeah. So based on this, I can know like how many datas are there. I can go and scroll it to see how much entries are there. There are around 4999, that is 5000 entries, which was starting from 0, which was starting from index as 0. So there are 5000 entries. So once I'm going to do that, I'm going to do then execute the head part of it to see the entire data frame, like how many rows and column I'm having, what are the things are there. Then I'm going to do the info of it to see the type of data type of each columns, like what are the data type is there of each column, how many total entries are there, how many total columns are there, so that I can go and find it from this doing info. So on this data frame, if I'm going to do a describe, so this is going to return me the statistical info of the data frame. So this statistical info of this data frame, it will going to give me, so in this data frame you must be seeing address has been excluded. So in this, the first, when I did the head, it included all the columns, and it included all the columns, but in this statistical information, this data this address column or the feature has been excluded, so which was the normally in the string format. So once that is done, we can go and do a column to basically check the spacing between the character in the column name. So this we can check it from here. So once that is done, we can do the entire pair plot using the Seaborn, and we can pass the entire data frame to visualize it and to see like how we can visualize and see the thing. So in this I can show you like this. So this was my histogram, like my histogram was like distributed my statistical uh, information, my segmented data, so which was there. So based on this, yeah, so based on this, I got the correlation, I got the histogram, I got the scattered plot which was distributed along this. Like I pass the entire data frame. Once that is done, I will to do this plot of my price which I am about to predict it. So once I'm going to do that, then I can see that my data frame has been kind of the price is been between 10 like 1 to 1.5 million, which has been uniformly distributed. So once we're going to found that, we're going to find the correlation of the column. So once I got the correlation of the column, so this is the way we do the correlation. If we want to pass that in the entire heat map, we can directly check like how the data has been distributed with n0s2. If we don't pass it with for the lowest scale, like the gray values and the low correlation, we won't able to see the data. But yes, we're going to, it would be based on the like the color scale control, it would be like that. Then we're going to go and do the columns. So basically we did a column here to check like what are the column we need to include or exclude as part of independent variable. So this was my independent, and this was my dependent variable, which was I want to predict it. So once I got this independent and dependent variable, like let's say for this y I got the value of price, and for this x I got average area income, average area house age. Apart from address, I got all the column which I had kept basically. Yeah, see this part, 1 2 3 4 5 5 columns. So I got the 5 columns here. So I stored that in x and y. So once that is done, now it's time to split the data. So there's a module already available for it, train split data. I want to execute this. So once split data is done, I'm going to split using the inbuilt API from the scikit-learn. I'm going to split the data. Then it's time to import the linear regression and instantiate it. Then I'm going to do the linear regression. Once I'm going to do this part like the, and I'm going to store that in the LM part. Then I'm going to fit the our train data in the linear regression. So once this part is done, I got this linear regression as an output, like I got this part. So it's time to now find the intercept of it, which was my let's say C. So I got the C. So once I got the C and y equals to mx plus c, so I need to go and find the coefficient of the model with all the features. Let's say for the multiple value of x, means for all the columns I need to go and find the coefficient of it. So once I'm going to find the coefficient, I'm going to print it and I'm going to analyze it more, like how my data has been there. Then it's time for the prediction. So basically prediction we normally do on unseen data. So X test is my ancient data which got splitted from this splitted train test split. So based on the values of X, I'm going to find the value of Y. So I got the prediction here. So once I want to do that in the scatter plot. So based on Y value, like unseen data and the predicted value, I got the scatter plot to do any kind of analysis to see how my data has been predicted. So for this white test, I want to do a desk plot to see based on my prices how my price got distributed on the unseen data. So that is basically with the, this is was kind of a residual histogram which we had found. So once that is done, so it's now it's time, the last part would be knowing the accuracy of the model, like what we had done. So for that this matrices is already available, this model is already available as a matrices in the scikit-learn. We directly need to import this AP, this module, and we need to call the API for each of it, like mean absolute error, mean square error, root mean square error, and the R square, and we can see the values of all of it. So yeah, this part. So by this we are done with the house price prediction. I hope you understand this. Now the next part would be understanding with the second use case to see the value of, to basically predict. So now the second use case what we would be saying, that would be the web app marketing prediction. So in that, let's say I got an contact from the e-commerce company, that is selling me something. Like let's say I got a contract from Flipkart, which they asked me to decide whether to focus their efforts on either mobile app experience or their website. So they hired me, as in they asking for the solution, like in which way we should expend more and which way we should go. So for that, like in this particular use case, we're going to predict based on the data set, either the company should focus more on either app or website. So let's start with this. So as usual, the first thing what we're going to do is like we will going to import the libraries. Once my library I got imported, so I'll going to read from the CSV what my data is there. Then I'll going to go and check the head where I can see for all my columns, like for my all my columns, whatever my data is there and in what format is there. Like for example, in this sense, 1 2 3 4 5 6 7. uh, for doing this head, I am getting 7 columns. Email ID 1 2 3 4. So there are total 8 columns, and these are the number of, like for the each user. This is the email ID, this is the address, this is the avatar what they had kept as an DP, average session length, how much time they spend on the website, how much time they spend on the app. So time on the website. So this was an average session in every day, kind of how much average session they used to give, length of the membership, like how long they hold the membership of this particular e-commerce company, and the yearly amount is spent, like how many orders they do from this particular e-commerce company. So all this data we're going to get it through, we can visualize or we can see it through by doing customers.head. Once we're going to do that, then we're going to go ahead and we're going to do this describe customer.describe. So basically customer.describe we're going to give me count, mean, steady, mean 25%, 50%. So this would be kind of statistical data which I would be getting, and here it would be only the numeric format, like which with the data in the numeric format we would be getting. Note this, like address and email have been address, email and avatar have been excluded from this data, or let's say from all this column, this three had been excluded. So once this is there, then we're going to go and do the info of the data frame which we had taken as customer. So we can see there are total 500 entries with 8 columns with email, address, avatar, like all the data type also we got, like for all the columns or the feature, what kind of data type is there. So we had now done with checking with our data, how we can check the data with the data set which we had loaded. So once that is done, we're going to do a kind of exploratory analysis on our data by visualizing it. So for this, we're going to use the Cbond. So first, I'm going to do a joint plot. So this joint plot basically would be the number of time spent on the website with the and yearly amount spent. So basically it would be comparing time on the website and the yearly amount spent columns. So basically we need to check out, like is there would be any correlation which we make sense with this data. So on executing this part, so we can see data are very scattered, few are very outliners. This data point we can consider as the outliner. These are two very far away from the most of the data points. So this doesn't make any sense. So for the same, we're going to do this we did with the website, then we're going to go and do ahead with the app. So then we're going to see on, we're going to plot our time on app on the x-axis, which will be my independent variable, and y would be my yearly amount spent. So for this, when we're going to execute it, we're going to see here the data makes sense, like few of the correlation happen here, and for this correlation few of the data set is been in the middle, but it's not too much correlated. So after seeing this, the first thing would be there, like I would need to go and directly check like whether the time on the app like how much time on the app which I am doing, whether that makes sense with the other kind of columns or not. So for that, the first thing we would be go and do is the time on the app based on the joint plot. We're going to see, like on the 2D hex bin plot, we're going to compare and see whether that make any sense or not. So once we're going to execute it, so you can see here, this is my time on app and this is my length of the membership, but it's like kind of scattered data and few data have been outside. These are the outliners which you are seeing here. So most of the data is scattered here, which this also doesn't make that much sense. So then we're going to do a complete pair plot of this entire data frame. We're going to pass the entire data frame customer to this pair plot in the Seaborn to see which all the columns exactly make a kind of correlation. So based on a system performance, this takes some time. Yeah. So by seeing this particular data, you can see this histogram, you can see this correlation and the scattered plot. So this correlation you can directly see here. For the two of the column, for the first would be length of the membership and yearly amount spent. So this data, this two columns make some sense, and the length of the membership with the yearly amount spent. So these two data, like for the yearly amount spent and the length of the membership, this have kind of a diagonal polynomial relationship, which is kind of a continuous variable, which makes sense for us to predict based on the plot what we looks the most correlated feature with. So the length of the membership makes the most of the kind of sense for this kind of length of the membership, you can say, for the yearly amount spent against the yearly amount spent makes the like kind of more correlated feature. So once this we had done, like from visualized data, once we found that this length of membership makes kind of more correlated feature against this yearly amount spent, we can directly go and create a plot out of it. And for that, creating the plot using the Seaborn, you can directly go and run. So you can see this is my plot, in that most of the like what we had seen here, what we are seeing here is basically the same data we had visualized it. So now it has been confirmed, like the length of the membership and the yearly amount spent, so that have directly kind of correlated feature linked with it. So the second part would be going and testing the training and testing the data. So now the what we need to focus on, what we need to predict is like the yearly amount spent, like what in what feature we need to predict, in what particular column we need to spend more, either app or web, like where we need to spend more. So for that, my predicted value would be, like we can say as an independent value, it would be yearly amount spent. So y would be for this customer, for this data frame, for this column yearly amount spent, this would be my dependent variable and this would be my independent variable. So basically in my independent variable, I would be taking the average length, average session length, time on app, time on website, and the length of the membership. So, and I would be excluding all the other columns such as email, address, avatar. So all these three I would be excluding it, and based on the 1, 2, 3, 4. So this 4 would be my kind of independent variable, and the yearly amount spent would be my dependent variable which I want to predict. So once that is done, I'll want to go and split my data as previously, like what I had explained, using the scikit-learn library, which they give us the module like train, test, split. So based on this, I will going to assign x train, x test, y train, and y test. So I'll want to go and execute this part, this part, this part. I want to import this library, then I will want to assign the external matrix. So once that is done, then finally I will going to go and import the linear regression from the scikit-learn library. Once that is done, I want to create the instance of the linear regression. Once that is done, I'm going to fit my training data, whichever the training data, X train and Y train, which I had separated it. So I'm going to fit my training data in my model. So this is going to give me an output like kind of linear regression method kind of thing, but this is like giving me an output saying my train data for X and Y had got fit for this model. So once that is done, I'm going to go and find the coefficient of it. So on finding the coefficient for each of the column, so I got the coefficient for each of the column. Now it's time to predict the test value. So like as I explained you before, in y equals to mx plus c, so this coefficient relates with the m. So we got the m. Now it's time to go and see the c of it. So similarly, in the if we need to find the c of it, then we need to find the intercept. We can directly call lm underscore intercept to get that particular value of c. We can go with that. So once that is done, we're going to go and do the predict based on the unseen data which we had already exploited it. So on doing that, I got the prediction. So this would be holding the value of the y, which this we can say as the yp, which got the predicted value. So once that predicted value is done, I'm going to kind of this so in this basically now I'm going to go and kind of do a kind of scattered plot for this, like for the unseen data and the predicted value and the predicted data. So this would be my y of like the which were the actual value which are there, and this would be my the yp, like kind of the predicted value which I had got. So based on this, I'm going to plot the label. So my x test, my unseen data would be my in x-axis, my predicted value would be on y-axis. So based on this matplotlib, I'm going to plot this. So once this plotting is done, I can clearly see most of the data has been aligned nearly to each other, which make sense, like model is more accurate and it giving kind of perfect data. So I'm going to execute this part. So when this part is done, so now it's time to evaluate the model, like what's the accuracy of it, how we need to do it. So for that we had a scikit-learn, or like for the sklearn library, we need to import this module matrices. So once I'm going to import the model matrices, then I'm going to do MAE, MSC, RMSC, like the mean absolute error, mean standard error, root mean square error. And by this way we can find all the three like the error matrices. In this part I have excluded r square, even r square which we can find. I had already shown you previously, like this is a way to find the r square. Let's say I'm going to do that as well. So now I got the mean absolute error, mean square error, root mean square error, and the r square. So I'm going to exclude this part. So yeah, so I got all the values of this model. So based on this residual, so value looks good. It looks like it's fitting with the data. So now for this, I'm going to plot a residual histogram against the predicted value. So that would be my unseen data minus predicted value. So I'm going to do a kind of disploit based on the C-bond. So I can see most of my data has been assigned properly, has been in uniform. So for this, we got to know like how we did, how we can find how accurate my model is, how accurate my model is. We can find based on the evaluation matrices. We had predicted the data based on the unseen data. We had created the model. So once all this are done, still it's time to find out the answer to the original question, like from where we need to focus, either on the mobile app or in the website development. Still we didn't find that. So maybe even like as what we are suggesting, like that doesn't even really matter, and membership time, which is really important. So let's interpret the data in that way. So for this interpretation of data, if we are doing it, so kind of for the coefficient for all the columns, if we are doing it, we have the coefficient of it. So for this column, if we are doing it, the coefficient which we had got at around the average session length. If you want to analyze the coefficient, like how much my coefficient is, so average session length of that one particular person would be around 25. So this would be 25 minute. Time on the app is 38 minute. Time on the website is 0.10. That means users spend more time on the app rather than on the website, and that is directly been proportional to the length of the membership, which we had already found. So from this we can directly interpret, like there had been like if there would be one unit increase in the average session time, there would be increase in 25 rupees. If there would be one unit increase in the time of the app, there would be 38 rupees kind of spent on the time of the app. If there would be one unit increase time on the website, there would be increase of 0.19 rupees spent on the website. So from this, like company can either directly focus on, either now they need to focus more on their mobile, or they want to spend more on the website. From this data is clearly visible, like spending or focusing more on the app makes sense for the company right now. Based on the correlation what we had got, based on the coefficient for all the columns, we can directly make a match saying spending time on the app makes more sense. But it really depends on the company, like what they want to do it. So by this we had finished our linear regression, and we had understood like what kind of different linear regression was there. So next would be I would be exploring with the other algorithm and would be uploading soon. So guys, so with the end of this, please like, do share, subscribe Cupula on YouTube channel. So all the code snippets and the demo would be available on cupula.com as well as on my GitHub profile. So this is my GitHub profile and this is my Cupula. I would be sharing the link as well as in the video description. So you can go and check that out there. Till then, goodbye. Thank you all.